This video lecture is concerned with continuous system modeling and is really designed to just give you a basic uh, concept of how to set up a continuous model in Awesome. We are going to work with just two state variables and in writing subroutine state we just define those two state variables simply. One of them is defined as a derivative, dd1, and ss2 is the second state variable, which should really be the same as ss1, but it's defined in a difference equation, SSL of 2 plus the rate times the current step size. And we're going to use a simple constant rate of 2 units per unit time. So you should see both SS1 and SS2 increase over time at a rate of 2 to 1. So at time 1, both of these variables should have a value of 2. At time 2, both variables should have a value of 4, and so forth. So you can, this is just to illustrate how you can set up function state. You have to number the state variables in order, put all the DD equation state variables first and all the SS equation state variables last. So in this case, DD1 is the derivative of SS1, and we just simply express it as the rate. In this case, it's 2.0. SS2 is the same quantity, but we refer to it or express it as a what's called a difference equation. We look at the last value of SS2, and then we add to that the rate times the current step size, dt now. So this will increase the last value by this amount of the amount contributed by the rate over this time unit dt now, and that is the way we compute the new value of SS2. So every function state looks like this. It's pretty simple to set them up. Again, don't forget to put all your DD equations where you're going to express a state variable as a rate first, and then put the SS variables last. So that's all we have. You don't forget the header information, vslam.h. Include the math library. We probably don't actually need it in this one since it's pretty simple. And pound define pi, that's left over from the Cedar Bog Lake example. Okay, let's look at the control model. Control model is also pretty simple. In this case, let's look at the continuous statement. This is the one statement that you have to add for continuous modeling. So in this model, we had one DD equation and one SS equation. So we tell Awesome that we have one of each. Pick the step size just at random. You can try any values you want. For a smooth function like this, we can actually put pretty good size step size and get accuracy. We'll get a warning if there are any out of tolerance calculations, and we're just going to specify an absolute error. So we're willing to tolerate this much error in the integration, and Awesome will use that in determining whether the step size was too big or not. If it exceeds error, then it goes to a half step, tries that. If that's satisfied, then it proceeds. Otherwise, it'll half the step size again. Okay. So you'll need to add this continuous control model to every continuous model you actually develop. Again, this part comes from how you represent the state variables. Everything else is kind of guess and try it, and as long as you don't get errors, then the values you've selected are fine. We're also going to use a record statement. Record statement is how we record information that can be either put in an Excel spreadsheet, an Awesome plot file, a table, a comma-separated file, database, or some user file that we define ourselves. In this case, we're just going to put it in Awesome, and we'll take a look at that at the end of the simulation. So we have one independent variable in the plot, time, or t-now. We're going to record samples between tt-beg and tt-fin. I'd like equally spaced samples, so I choose the interval. Otherwise, data will be collected every time the step size is updated, so we could get quite a few data samples. In this case, I just take a look at the state variables every 1/10 of a time unit, and that's it. So I'm going to look at SS1. Again, we didn't write an equation for SS1, we wrote an equation for DD1, which is its derivative. But Awesome integrates that for us, converts it to SS1, and we'll collect dependent variable observations on SS1 as well as SS2. We can specify a different format, but that's basically all we need to do. So that's the record function. We're going to specify we're going to run it a little over 2 time units. We'll stop at this time. We'll see what the integration looks like. So let's go ahead and run that. I click on this to actually run it. It's going to go through a translation process and compilation and link process automatically. And we can look at the output. In the output for state variables, you'll always get a state variable report on the current value. This is at time 2.1, so we have a current value for SS1. Okay, and since we expressed SS1 as a derivative, we also get the current value for DD1, which of course is 2, which was the rate parameter we specified. And at the end of the simulation, SS1 is 4.2, twice 2.1 since the rate is 2. And for SS2, we define that as a difference equation using the rate, but we get the same value. So it looks like things have run properly. We can look at the output report in intermediate results and check and see if we got any error messages. We didn't, so it looks like the simulation worked properly. And we can look at the graphical report since we selected an awesome plot. And we'll look at time versus SS1 and SS2. So let's look at SS1 first. And you see just a straight line since the rate is constant. So it increases at twice the time rate. So here at time 1, we have a value of 2 and so forth. And if we look at the same graph for SS2, should see the same thing, and we do. Okay, so that's just an example of how you model a simple continuous variable problem, a continuous simulation. The subroutine state's pretty easy to set up, and more complicated problems, even something like Cedar Bog Lake, this was pretty easy to initialize. Okay. Okay, that concludes the basic video, and we'll also have a video on the PowerPoint lectures on continuous modeling.